Hello and welcome to the Apache Cassandra Corner, a community-driven podcast for all things Apache Cassandra. The Apache Cassandra Corner is sponsored by DataStax. I am your host, Aaron Pletz. Well, hello everyone, and welcome back to the show. And today we have a special treat. We have Jonathan Ellis as a guest on the show. Jonathan, welcome. It's so great to have you here.
Thanks, Aaron. Great to join you.
Yeah. So, I mean, for those of us, it'll be few as far as our target audience for this podcast goes. But for those of us who may not know who you are, why don't you tell us a little bit about yourself?
Oh boy. Well, the short version is I started DataStax 13 years ago to commercialize Apache Cassandra.
Excellent. Excellent. So before that, you were at, I'm trying to remember the story. You're at Rackspace, right?
Yes. Yeah. So the story is that Rackspace hired me in the fall of 2008 to build them a scalable database, because this was back when Rackspace had a plausible shot at competing with AWS as an equal.
Right.
And so they said, hey, we're going to need a scalable database both to sell to our customers and also to scale their internal systems. And so I was kind of in charge of doing this with a shoestring budget, and both because of just by nature, I don't like spending time solving problems that have already been solved. And so my usual approach is to reach for what's out there in open source and how can I contribute to that and make it better. And also because the budget was for maybe 3 engineers total. So it's like, okay, obviously we're not going to build something from scratch with that small of a team. Right, so I was evaluating the scalable database options that had started to appear around that time. So you had HBase was out and MongoDB was out, and some other things that you don't hear about anymore. Project Voldemort from.
I was going to say Voldemort. Yep.
Yeah, and which I saw just recently that they mothballed the project. Been on life support for a while. Dynamite by a really good engineer named Cliff Moon, and Facebook had open sourced this thing called Cassandra, which took the shared nothing design of Amazon's Dynamo and married it with the structured storage of Google's Bigtable. And so I was really attracted to this because it was powerful, but it had a pretty small surface area. So at the time, if I remember correctly, Cassandra was around 35,000 lines of code. And by contrast, HBase was closer to 250,000. And so I was like, okay, I can actually dig into Cassandra and start making things better in a relatively short amount of time. And I don't see that being possible in the same way with these other options. Right. And I really liked the marriage of that shared nothing design. Plus, you do need more than key value to build reasonable applications. Like if the database isn't going to give you structured rows and columns, you're going to have to kind of layer that on somewhere else. And so I liked that was built into Cassandra. So started working on Cassandra. Facebook had not initially, but over the next few months, they contributed it to the Apache Software Foundation. Right. And then for people who are familiar with the ASF, new projects go through something called incubation. And part of the goal of incubation is to make sure that it's not, there isn't a bus factor of 1 on the organizational side. They want contributors to the project from more than one company. Right. And so when that happened, I went to the ASF mentors and I said, hey, I'm the closest thing you've got to an expert on Cassandra outside of Facebook. And so I became a committer and then eventually project chair when we graduated from incubation.
Right. Yeah. Again, another part of that story that I've heard is that, you kind of made the decision at some point to leave rack space and then build something that was, sustainable around the Cassandra project. And that's kind of how DataStax came to be. Now, the co-founder of DataStax was Matt File. Did I say his name
right? That's right. Yeah.
Yeah. And again, the story goes that he came to meet you for lunch or something with the intent of talking you out of doing this, and then somehow it ended up going the other way around.
Right. So I was leading the small Cassandra development team, and Matt was leading the team that deployed infrastructure like Cassandra across rack space. And so that was his interest in it. That's why he came down to talk me out of it. And I said, actually, I'm looking for a CEO, and he decided that was worth doing with me.
That's awesome. That's awesome. Yeah. So yeah, I mean, I've been around the project, long enough that I've heard bits and pieces of this, but yeah, never the story directly from you. So that's pretty cool. Thank you for that. So hey, let's fast forward. Okay, a bunch of years. To earlier this year, we're looking at things like Gen AI starting to pick up steam. We've got AstroDB, out in the cloud, and you kind of take a look at the landscape and say, hey, I think we could integrate vector search or build vector search into Cassandra. So yeah, kind of talk us through a little bit of that.
Yeah, I think multiple people at DataStax were thinking along these lines at the same time. The first one that I saw was Zhao Yang, who's also a Cassandra committer, saying, "Hey, vector search looks like a really good fit for Cassandra." And so, as it turned out, nobody else was available, so they asked me to see what I could do. Yeah, I mean basically the short version is started hacking it into Cassandra, realized that among other reasons, we wanted to be able to leverage the Project Panama SIMD acceleration that you get in recent JVMs. And any code that gets committed to Cassandra has to support back to JDK 11. And so it made more sense to put the vector search functionality in a separate module that could be built separately and pull in the right implementation at runtime. And so that's how JVector was born. We put that in a project called JVector, and I'm fairly confident that it's the most advanced embedded vector search engine in the world, and certainly for Java.
Right, because yeah, you didn't actually start with JVector, right? It was Lucine's HNSW.
Oh man, you want to dig into all of the history? Yes, yeah, that's correct. So the initial version was, hey, we can plug in Lucene and call it a day.
Right.
We already have Lucene as a dependency for SAI. So, although it turns out that wasn't quite as easy a lift because SAI was using Lucene 7.5, and then somewhere along the line, they decided that Lucene data files should be Little Endian based instead of Big Endian, and that broke everything. So the upgrade was a heavier lift than it looked like at first. But yeah, plug in Lucene, call it a day. There's a couple problems, but the main problem is that Lucene's implementation is single threaded. It's not thread safe, and you can't easily make it thread safe by throwing in a synchronized block or two without torpedoing performance.
Yeah.
And so we were going to need to move beyond HNSW because HNSW, we should probably talk about what that is in a minute, but HNSW performs poorly when you can't fit all the vectors in memory. We're building this into Cassandra, but we're also building it into Astra, our multi-tenant cloud service. And so we care about larger than memory workloads. Even if your workload isn't larger than memory, we're going to stuff you into a bunch of infrastructure with a bunch of other tenants and until we start hitting performance limitations, right? We want to maximize what we get out of that infrastructure footprint. So for multiple reasons, it made sense to spin what we were building out into this separate project. So that's where JVector came from.
Oh, excellent, excellent, and of course, I mean, JVector is running great now. You know, I've been using it on Cassandra's Alpha 2 build, and it's been, you know, I haven't seen any issues with it. I mean, granted, you know, on my own laptop, I'm probably not going to see a whole lot of performance issues, but yeah, it's been nice and solid for sure.
Thanks. Yeah, we actually did have some issues that we didn't find until production, but I mean, for multi-threaded core code that cares about performance as much as JVector does, I think we did a pretty solid job, and haven't had any bugs reported in several months that were JVector's fault, at least.
Well, excellent, excellent. And you know, one part of you know, the JVector implementation that you know, I don't know if I've had a problem understanding it, or if it's just not exactly clear how it works. But you know, I'd like to hear more about the implementation of like the disk affinity from the paper that I think it was the paper that Microsoft published. Right, right. Yeah. How does that kind of play into it? And not an easy answer. Huh?
Normally, to explain this stuff, I have a whiteboard or at least a slide or two, but we'll see if we can make it make sense. So broadly speaking, everybody who's trying to build a general purpose vector index uses graph algorithms,
right?
Because that lets you build your index and search it as it's being built incrementally. The partitioning-based algorithms all require you to know your entire data set ahead of time. So that's, you know, if that might work for a Lucene, and that's not what Lucene does, by the way, but for Lucene, it could work because Lucene has this concept of commit, where it says, you give me a batch of data, and then I index it behind the scenes, and then once I commit it, which means turn it into a searchable segment, then you can send me queries.
Okay.
But for you know, a database like Cassandra, or for PostgreSQL, PGVector also uses HNSW. You want to be able to index things immediately and have them visible to searches immediately.
Right.
So that's the main benefit of the graph category, is that it lets you have that immediacy. So one of the first you know, steps towards modern graph approximate nearest neighbor search indexes was called navigable small world. And what that means is that I'm going to build my graph in such a way that it's navigable, meaning that if I start at my entry node, I should be able to reach every other node I've ingested. Like if there's some of my rows that I will never see in a search, like that's bad, right? We want to be able to find them if they're there. So it's navigable, but it's also a small world, meaning that we're going to try to reduce the degree of the graph. We're going to try to not include edges that don't help us. And the reason why we want to minimize the number of edges is that every edge you have slows down your search. So you better have, you need to make those edges count. And so the authors of NSW said, here's an algorithm that will allow us to predict which edges are going to be most useful. And so then Yuri and I think his co-author Dimitri in HNSW, they added an H for hierarchical. And so they did two things. They refined how they chose those edges, but then they added the hierarchical part, which means that you have a graph in an HNSW index that contains all your vectors, but then you have another layer above that that has 10% of your vectors. And then you have a layer above that that has 10% of that second layer. and then 10% the next. So you're reducing by a factor of 10 roughly every time you go up a layer. And what that does is it lets you start your search at the highest level and find the closest match there. Use that as your starting point in the next level down. Find the closest match there. Use that as the starting point. And so that lets you kind of make these large jumps across the graph, across edges that aren't directly connected in the lowest level, but in the higher level they are because it's sparser.
Right.
So that's HNS-W. So
HNS-W, yep.
And that's published in 2016, and then 3 years later, Microsoft published the DiskANN paper, and so they made two changes to HNS-W, one of which is significantly more material than the other. The two changes are, first, they said we don't need those extra layers. We're going to flatten it out. And here's how we can build those long-range edges into our graph without adding extra layers. So that's fine. It simplifies things. Simple is better. And actually, when you're building a concurrent implementation, that actually makes a really big difference in how simple it gets. But from a performance standpoint, it's kind of, you can find data sets that work better with one, data sets that work better with the other. It's neither one is an obvious better pick from a performance standpoint. So I'm happy to go with the simpler one if it's roughly as performant. But the performance benefit, the performance gain that you get in DiskANN comes from the other change that they made, which is that instead of searching against the raw vector as we scan through the graph, let's compress the vectors, and we'll store the original uncompressed version on disk, but we'll keep the compressed version in memory. And this is a lossy compression. So it's like going from TIFF to JPEG, right? You're hoping that your approximation is still meaningful and useful, but you've lost some amount of information.
Right.
So the idea is I'm going to do my search with this lossily compressed version, which is called product quantization. That's the compression algorithm.
Okay.
And it's because you're doing that. You've compressed it by a factor of 16 or 32. Even if you're doing an in-memory search, you're coming out ahead. It's faster to search the uncompressed because they're shorter. When you're comparing vectors, it's a big O of n operation where n is the number of dimensions of the vector. So if you can compress it down, then it's a faster comparison. And so you can spend some of that performance that you've gained by doing that compressed comparison. You can spend some of that and search deeper in the graph than you would have. And what that does is it lets you make up for the accuracy loss that you have using those compressed versions. You can search deeper. So instead of saying, say, 100 raw vectors, I'll look at 200 compressed vectors, and then the best options that I come up with, I'll resort those with the original uncompressed vectors that I pull off of the disk as I'm doing that breadth first search, because I store those raw vectors interleaved with the graph edges, which are stored as an adjacency list.
Wow.
Yeah. So that's DiskANN in 5 minutes.
I was going to say that was pretty cool that you were able to distill that down that much. That sounds like it'd be quite the improvement for sure. Yeah.
So what we saw, so we kind of torture tested the HNS-W implementation, right? We deployed that in Astra, and in fact it went GA before JVector DiskANN was ready.
Right.
So we loaded 400 or so million Wikipedia. So we're using OpenAI. I don't remember which embedding algorithm we were using, but we had 400 million of these vectors that we loaded in. And the profile flame graph was like, there were no flames. It was just one huge block that said, I'm reading vectors from disk. Like that was 95% of the performance profile.
Yeah.
Uh,
Yeah.
so when we moved to disk ANN, we got roughly a 30x performance increase from saving 90% of those IOPS and doing
Right.
the
Right.
searches with the compressed versions.
Wow. Yeah. I mean, when you put it that way, you're right. I mean, your disk is always going to be a bottleneck, especially when you're going to, when you're using it to pull back so much of your data like that. That yeah, if you can offload any of that into RAM, like JVector does, I mean, yeah, that's going
and
to be
it,
a
and it,
boost for
and
sure. For
it's
sure.
not just about the quantity, right? But it's
Mm-hmm.
because that
Mm-hmm.
you're doing random accesses. When I'm traversing the graph, every node is almost equally likely to be visited. And so
Right.
it's not like a B tree or even an LSM where you can say, oh, 80-20 rule, most of my hot data is going to be in these places that I can cache. That
Mm-hmm.
doesn't work
Mm-hmm.
for a vector index search.
Yeah. Wow. Well, hey, yeah, thanks for explaining it all. That's awesome. That's definitely quite the deep dive for sure.
Yeah, I mean, and if anyone wants to work on this stuff with me, we're hiring, and it's super fascinating because those dates I mentioned, 2016, 2019, like this is really recent stuff, and
Yeah. Yeah.
we're working on problems like what's the best way to spread a really large index across machines, or how do you do compaction of really large indexes, or how do you build an index that's larger than memory in the first place? Like
Right.
there's
Right.
the industry and research community collectively have some answers to these questions, but none of them are very good answers. And so we collectively have this feeling that there's work to be done here to find those better answers. And so it's a really exciting place to work.
Yeah. Yeah. No kidding. No kidding. All right. So, hey, before we close up here, let's fast forward a little bit. In a couple of weeks, we're going to have our first Cassandra Summit in quite a few years, actually. And there's going to be great talks there, from with folks from like Apple and Netflix, and many other places as well. And of course, we've kind of like merged with the AI Dev Conference, so there's going to be some discussion there as well on like reg and gen AI, and building things with LLMs and using vector search. There's just so much there. So Jonathan, if there's something you could say to our listeners to maybe incentivize them to want to go to the summit, what would that be?
It won't be as cold as Chicago.
Well, that's fair. Yeah.
No, I mean, I was gonna say I was gonna try to pick my number two favorite tech conference besides Cassandra Summit. I guess let me put it this way. For me, the sweet spot of an in-person conference is around the 800 people level, maybe 8 to 1,200 people,
Yep.
because that's big enough that you get a wide variety of people attending. You have a lot of perspectives represented. Uh, but it's also small enough that you can recognize people that you've seen before and say hi to your old friends
Right.
and
Right.
have some interesting birds of a feather session. By the time you get to like the 5,000 person conference, it starts to feel impersonal, in my opinion.
Right. Mm-hmm.
And so what we're shooting for with the Cassandra Summit is like right around that sweet spot. And yeah, I think that for those of you who've been there before, you know what I'm talking about. And if you're thinking
Yep.
of going
Yep.
for the first time, then you'll make friends that you'll remember and be able to see again and again.
That's a good way to put it, for sure. Because seriously, that's the number one thing I'm looking forward to as well. I mean, the tech is cool, but it's going to be great to see people who have been around the community for years and catch up and find the bottoms of a few beer glasses. That's that's what I'm looking forward to most. It's just seeing everyone and catching up with them. So yeah, I concur. All right. Well, hey, Jonathan, thank you so much. This has been great. And for those of you, who are still with us, you listen through this episode and got a complete treatise on digging into J vector and disk ANN, and yeah, I mean, this has been really great, Jonathan. So seriously, thank you for coming on.
Thanks, Aaron. Glad to be here.
All right, everyone, that's it for today. It was great to have you all on, and we'll see everyone at the summit. And that's all for today. Thank you for listening to the Apache Cassandra Corner. Apache Cassandra is a registered trademark of the Apache Software Foundation. Thank you, and have a great day.